Okay. Hello. I'm glad to give a talk on this workshop, and in my talk, I will present some results on decomposition of the gauge field in maximal abelian gauge. This work was done with my colleagues, which you can see on this slide, and I will talk about maximal abelian projection and abelian dominance, about monopole decomposition, and some results on the composition of static potential and in SU2 gluodynamics and SU2 QCD, and some results on decomposition and in SU3 gluodynamics and the composition of some other observables. This work is closely related to dual superconductor scenario of confinement. It first was formulated by 't Hooft and Maldestam. In this scenario, roles of electric and magnetic fields are interchanged, and a precursor string appears due to condensation of color magnetic monopoles. However, rigorous proof of this scenario is yet to be done. That's why we investigate its validity on lattice. And to investigate it on lattice, people use maximal abelian gauge. Here you can see the first formula. It's a gauge condition in SU2 case in differential form. And to solve this, one needs to minimize functional, which you can see, and then one needs to make an abelian projection to obtain some observables. You just take diagonal part of SU2 field. There's abelian dominance hypothesis, which tells that if you do decomposition on diagonal part, which is U small, and non-abelian part, which is C capital, you may obtain approximately equal values for infrared observables on a lattice. If you use only diagonal degrees of freedom instead of original SU2. First numerical results were obtained by Suzuki and Yotsuyanagi in 1990. They did it for observable of string tension between two static quarks. On this picture, you may see plot from article of Bari et al. It shows potential between two quarks in SU2 gluodynamics. One can see that linear parts of this potential of abelian and original SU2 are approximately equal. However, values at small distances of potential are not. This plot demonstrates abelian dominance, that if you do maximal abelian gauge and take only a diagonal part of original degrees of freedom, you may obtain approximately the same physical observable, in this case, string tension. After fixing maximal abelian gauge, diagonal part has monopoles, color magnetic monopoles, which can be obtained by the Grant-Sun procedure. We follow the idea that if we take only degrees of freedom which contain monopoles, then we can decompose our original diagonal part into photon part and monopole part. Monopole part can be obtained by first formula, and photon part is just difference between original diagonal part, theta, and monopole part. Also, we decompose our original field in two parts: monopole part, U small monopole, and modified. Modified is just original field with monopole part removed, which does not contain monopole, at least really few monopoles. Before us, this modified part was considered only in one paper, and that's why it is carefully considered in our simulation. Now let me present you a plot from Bali et al. Article. It represents these decomposition on monopole part and photon part. You could see abelian potential, photon potential, and sum of monopole and photon potentials. One can see that sum of monopole and photon part is approximately equal to abelian of diagonal part. This represents the idea of monopole decomposition. However, now let me move to decomposition on some result of decomposition in SU2 fluid dynamics and SU2 QCD. We used observable potential between static quarks, which obtained from Wilson loops. And as I said before, usual representation was to decompose onto off-diagonal part, C capital, and monopole and photon diagonal parts. However, in our work, we consider another representation to decompose onto modified part, which does not has monopoles, and on monopole part. And we demonstrate that potential between static quarks, original potential of SU2 field is approximated, well approximated by sum of monopole potential and modified potential at all distances, not just string tension, but all distances of potential. On this slide, you can see results for SU2 gluodynamics for zero temperature and different beta. Increasing beta means decreasing lattice spacing. One can see that, yeah, on these pictures, you can see SU2 red potential and green sum of monopole in and modified. It can be seen that relation is well satisfied for all betas. And moreover, by I, it can be seen that with decreasing lattice spacing, this relation becomes more exact. More clearly, it can be seen from this plot, where delta is a relative deviation. It's a difference between red and green potentials divided by red potential, by original. It's difference between original potential and sum of monopole and modified. It can be seen that with increasing beta or decreasing lattice spacing, difference reduces. Also, we checked universality. This plot shows potential for the same SU2 gluodynamics, but with improved action. Although this relation is not that well satisfied, but this is because lattice spacing is bigger than in case of previous plots that with non-improved action. Also, we did some simulations for SU2 QCD with quarks. In this case, relation is also well satisfied. Now let me move to non-zero chemical potential. This is also SU2 QCD, but with quarks, with staggered quarks, with non-zero chemical potential. One can see that relation is also well satisfied for all of them. Although for zero chemical potential, there's a little discrepancy between original potential and sum. This may be due to lack of statistics, or due to not that well done gauge fixation. I will investigate this question later. Now let me move to decomposition in SU3, gluodynamics. It was done, you may see lattice setup below plot, and on plot is the same potential between static quarks. Relation is also satisfied. Also, this idea may be checked on some other observables. We did it for static potential in a joint representation. Although difference is quite big comparing to potential between quarks in a fundamental representation. And it should be carefully investigated later. And also flux tube, which is color electric squares of color magnetic and color electric fields between static quarks. It can be obtained on lattice using correlation of Wilson loop with plaquette. And usually people study sum and difference of electric and magnetic fields, which are energy density and action density, which you can see below. However, because to obtain energy density, you need to take a difference between two operators, it contains huge statistical errors. That's why in my talk, I only present results on action density. It was done in SU2 gluodynamics for different bases also. And one can see that sum is sum of action density for original SU2 fields and sum of monopole and modified. That original flux tube for original SU2 degrees of freedom and sum of monopole and modified is approximately equal. And it can be seen by eye that with increasing beta, this relation becomes more exact as well. However, it needs to be investigated more carefully. This leads me to the end of my talk. And to conclude, we demonstrated that relation for static potential holds for various theories for SU2 Global dynamics, SU3 Global dynamics, and SU2 QCD. And with increasing beta and decreasing lattice spacing, it becomes more exact. It might be exact in continuum limit. There's an indication that it might be exact in continuum limit. And also similar relations hold for flux tube and adjoint representations. In future, our next steps would be to check this relation in full QCD and also consider non-zero temperature and maybe higher values of chemical potential. Also, it needs to be rigorously explained. To do this, we may try to study correlations between modified and monopole degrees of freedom. Thank you for your attention. If I have any questions, I'd be glad to answer.
Thank you. And are there any questions? Okay, I have just once. You have any idea why the adjoint case is work worse than the fundamental one for SU2? And that was just the lattice spacing. Have you checked also the dependent on the lattice spacing to see if just by chance is large in this case?
Well, first of all, we don't know yet. We need to check with different betas to understand the reason why this relation doesn't hold that well. In this case, yeah.
Okay. Are there any other questions, both from here or from remote? I don't see nothing. So if there is no other question, let's thank the speaker again. Yes, so we'll